Estás viendo Canal América, televisión dominicana para el mundo.
A Time for True show is sponsored by the Office of Dr. Bernard Fialkoff, a periodontal, dental implant and laser specialist in New York City, for over 40 years. Dr. Fialkoff was honored by the International College of Dentists and Pierre Fauchard, and received the Presidential Lifetime Humanitarian Honor from the White House. Call us at 718-229-3838.
Sometimes life can be so damn hard. You don't know where to go. Everything keeps falling apart. Yeah. You try to do your best, but only God knows that you've given everything you've got, but the world takes you down. You just keep moving on. Let your fears.
Welcome to A Time for True show. I'm your host, Dr. Bernard Fialkoff, and I welcome you back to our program. And tonight we're going to cover something really very important to the future of our world, of humanity. And we've seen so many movies in Hollywood about this in the future and what happened when we didn't really pay attention. We didn't really change things for the better. What are we talking about? We're talking about climate change, global climate change, which affects all of us, all of our countries, all of our families, the future really of this blue planet. And we're very lucky to have with us tonight Dr. Samuel Miller, PhD in Buddha. Let's introduce him, put his images up on the screen. Dr. Miller was actually trained at Chanute Air Force Base, where he received his training in weather forecasting. He has a Bachelor of Science in Physics. He has a Master of Science in Earth Science Oceanography, and a PhD in Earth Science from the University of New Hampshire. He earned an MBA from Plymouth State University, and prior to joining the faculty there, he worked as a meteorologist for the U.S. National Weather Service in the Alaskan region. At the University of New Hampshire, he served as instructor, lecturer, and research scientist for the Climate Change Research Center. And he worked as a contract weather observer for the Peace Air National Guard Base Weather Station in Portsmouth, New Hampshire, and as an active duty weather forecaster for the U.S. Air Force at Adana, Turkey, Plattsburgh, Travis, and Loring Air Force bases. In addition, he teaches at Plymouth State University, and he's a certified consulting meteorologist and serves on the AMS's National Board of Certified Meteorologists. And we're very lucky to have him with us, and we want to bid a warm welcome to Dr. Samuel Miller to A Time for Truth show. Welcome, Doctor.
Thank you, Dr. Fialkoff. Happy to be here.
It's a pleasure to have you. You know, the topic you're going to discuss is so important. And first question I had is, when you were a young guy, were you always interested in climate change?
Now, I was a young guy in the 1960s, and nobody was really talking about it very much back then. So I think I was always interested in, I think in those days the term was ecology or environment, but climate change, no, that came along later.
Okay. And you know, in all honesty, you have so many varied opinions. Some say it's just economic, some say it's political, some say it's some kind of earth cult group. Some people say, well, it's just to scare you into appropriations. Some people say it's just a lot of different philosophies. But I've met you, I've spoken with you, and I know you're very objective professor, scientist, very trained. So what I wanted to do is Buddha, if you can put up his first image, and I wanted to ask you if you could, with our viewers, explain to us what's going on with climate change, what is the truth about climate change, and what needs to happen. Why don't you go ahead, engineer, please put up that first image, please. Go ahead, Doc.
All right. Well, listen, before we go into this, what you're looking at here is an ice core record from Antarctica. But let's just talk about where the origin of climate change, or at least our modern understanding of it. Where did it come from? It started with James Hansen, who was a graduate student in the 1960s working with Dr. Van Allen, for whom the Van Allen radiation belts are named.
That's right.
And Dr. Hansen was actually interested in studying Venus, and he was using radar observations of Venus to try to understand what was going on there. And he discovered that Venus was extremely hot, much hotter than you might have expected to be given its relative distance from the sun. And he realized that Venus was caught in a runaway greenhouse effect. And as he began to think about it some more, he realized that by changing the atmospheric chemistry of the Earth's atmosphere, that the same thing might happen here. And so he changed his focus to what was going on with the Earth's climate. And all right, so one of the first things that you hear from climate change skeptics is that all the changes that we've seen with the Earth's climate in the last 150 years are because of the cyclic nature of the Earth's climate. It is true that the Earth is in a cyclic climate pattern. That's been going on since the beginning of the Pleistocene, about 3 million years ago. So this ice core record, what you're looking at right here, is from the Vostok Science Station, run by the former Soviet Union and now Russia in Antarctica. And it shows a record of, let's see, for example, the top line, the blue line, shows the concentration of carbon dioxide in air bubbles trapped in ice going back through time. Across the bottom, you can see the age, the period of time. So it starts with the present all the way over on the left, and then going backward in time up to a period of about 450,000 years. And across the top, you see the equivalent depth of the ice. So this ice core goes down more than 3,000 meters. So this is a 10,000 foot deep ice core. It's about this big around. It's been drilled out of the ice, taken back to a lab, handled extremely carefully, and then analyzed for a number of different factors. So the blue line shows the concentration of carbon dioxide in the atmosphere at these different points in the past. The red line shows the corresponding temperature. And then there's some other stuff that's going on, for example, what's happening with the methane concentration. But if we just focus on the upper two lines, you can see that there's a very strong relationship between the carbon dioxide concentration. When it's high, the temperature is high, and the temperature record of that time. And so that means that if you know what the carbon dioxide concentration is, you know to a very high degree of certainty, and of course we understand the levels of uncertainty, but you know to a fairly high degree of certainty what the actual temperature is. So you can use the amount of carbon dioxide in these bubbles as a kind of proxy, as a way of getting the temperature number in degrees C. The other thing that you can see looking at that are the normal range of variation. For example, if you look over on the left side, looking at that blue line, you can see that right now, where it says 0, the number corresponds to about 300. That's in parts per million. It's a kind of how much CO2 is in the atmosphere. And that doesn't correspond to the beginning. That goes back several hundred years before the beginning of the industrial age. So you can also see that if you go back a little further in time, just a little bit to the right of that, that number drops back below 180. So that is the last glacial maximum, the last ice age. And you can see the temperature was quite low then too. And if you happen to be where I'm sitting here in northern New Hampshire, there was 10,000 feet of ice here. We were under a glacier. Now, of course, that only shows up in the wintertime. And so there's a number of things you can get out of this. You can see that it is cyclic. There are times when the amount of CO2 in the atmosphere is high, like it's 300. You can see several points in the past, over the last several 100,000 years, when it was high. And you can also see several points when it was quite low. So that's the cyclic climate. We think we understand what's causing that, but I think that would take more time than we had here tonight. The other thing you can get from that is the normal range in the amount of carbon dioxide in the atmosphere. During interglacials, like now, it should be about 300. And you can see that right across the line. You can see 4 interglacial periods going back in time across that blue line there. And during ice ages...
I'm sorry to interrupt you. How long does that interglacial period of high CO2 in the atmosphere last?
Normally about 10 to 15,000 years.
10
the
to
ice ages are
15,000.
about... So the current interglacial, called the Holocene, is roughly 12,000 years old. So it should be coming to an end. And
So
you can see that
we have about another 2,000 or 3,000 years.
well, that's assuming that these natural cycles continue.
Okay.
So the other thing that I want to point out is you can see that during the ice ages, it drops down to about 180. So that gives you the normal range between 180 and about 300. And this is from direct observational evidence. And you can find other ice core records that go back 1.5 million years, and they show the same thing. This cyclic pattern of warm and cold and high and low CO2 concentrations. There's a lot of physics.
I'm sorry to keep interjecting, but it's very interesting.
All right.
And so this high CO2 level is what some people call with the greenhouse effect. Is that wrong? Is that right? Or
I wish I could give you a yes and no. Unfortunately, we've only got 15 minutes to talk about this, and normally this takes a long time to explain. I wish I could do it in such a short period of time, but I can't. Here's the point I want to make. Right now, from direct measurements, we know that the CO2 concentration, is almost 425, as opposed to 300, which we understand to be the natural upper limit during the Pleistocene and then the Holocene.
yes.
So we know that we're well outside the normal range of variation in these cycles.
So we're higher.
We're way high. And the rate at which it's currently increasing is 100 to 200 times faster than the increase you see on this graph right here, from the last glacial maximum, when it was quite cold, to the interglacial period that we're in, the Holocene. So it's increasing much faster than it has. There's no natural explanation for that. And the numbers are on the order of, well, let's see, instead of 300, it's 425 parts per million. So it's a third higher than any time, even during an interglacial in the last million years, at least, probably much longer than that. So we are not experiencing a normal variation. We know that something has gone seriously wrong with the chemical composition of the atmosphere.
Is it safe to say then the CO2 correlates, I think you said earlier, with a warmer atmosphere? Is that correct, or did I?
Well, that's known for sure. That's been understood really since the 19th century. A gentleman by the name of Arrhenius, a Swedish scientist, and then actually another person, a woman whose name I do not recall, who came before him, but was not initially given credit for the publication, was the first to discover that CO2 is a greenhouse gas and that it blocks infrared light. There's been a lot of criticism about that, saying, well, that only occurs in a laboratory, but no, that's actually been tested in nature now. The Department of Energy got together with the University of Oklahoma and set up field stations in Oklahoma and on the Arctic Sea in Barrow, Alaska. It's not called Barrow anymore, but that's the last name I was able to pronounce for that town. And took measurements of CO2 and temperature and found that there's a very strong correlation in nature between the CO2 concentration and the temperature.
Very
so the short version is if you add more carbon dioxide to the atmosphere, it gets warmer, and it does it almost immediately.
Okay, now you have another image. So engineer, if you put the image up for us, please, so that the doctor, he has so much to cover. It's very interesting, very important. So we have a warmer atmosphere, we have more CO2, and the next image, Buddha, please. There we go. What is this, doctor?
This is a reconstruction of the Holocene in terms of its temperature variation relative to a reference period. So time goes from right to left in this case. So the current the present moment is all the way over on the right, and the past 12,000 years ago is all the way over on the left. And this shows the current interglacial, which we call the Holocene. And you can see that it peaked. The warmest point on here was between 6,000 and 8,000 years ago. And since then, it's been steadily getting colder over time, except in the extreme recent period of time. So this reflects, it's a close-up. It reflects what was shown in that ice core record earlier, except it's the most recent 12,000 years that's been spread out so you can see it in a lot more detail. And it's exactly what you would expect. Interglacials last 10 to 15,000 years. The current interglacial is about 12,000 years old, and it peaked about 7,000 years ago. And since then, because of cycles that are forced by some various astronomical effects, which we can go into if you like, the world has been slowly getting colder, reaching a point where it would drop into the cold, stable climate state. Except something in very recent times, you can see that the temperature took off all the way over there on the right. That is a result of human intervention and changes in the atmospheric chemistry.
Very interesting. So it's very high, because when I can see there on the far right, is higher than the highest peak in the center.
That's right. Now, there's a certain amount of uncertainty here, which gets larger as you go back further in time. And so the color fill shows you the uncertainty area. And then there's a heavy line in the middle that shows you kind of the most likely, or the median response. There are many different models at work here that have incorporated a lot of different types of data, and you combine them all in order to get an understanding of how much the uncertainty it is. But even accounting for that uncertainty, the present moment is warmer than at the warmest point in the Holocene 7,000 years ago.
Very interesting. Buddha, let's have the next image, please. Let's have the next image for the doctor, please. And now, what is this image here, doctor?
Okay, now this is a monumental reconstruction of the global climate going back millions of years. And there's a lot going on here. We could easily spend hours just talking about this graphic. You can see the reference across the bottom. I highly recommend people go and read this article. You can see, for example, the moment when the dinosaurs were killed about 66 million years ago. You can see another place where it says hothouse Earth. That was a point about 55 million years ago. Sometimes it's called the Paleocene-Eocene thermal maximum. And then we come up to the present, and again, time goes from right to left, so the most recent time is all the way over on the right, and you notice that the scale stretches out as you get a little bit further towards the present. You can see the Pleistocene, and you can see where there's this kind of zigzagging pattern in the global average temperature, which were ice ages and interglacials. And then it takes you right up to the present. And then finally, we have projections based on what are called representative concentration pathways, which are socioeconomic models of the amount of atmospheric CO2 and CO2 equivalents, other greenhouse gases. And there are several different models of this, but if you've got a minute, I'll just let your viewers know that we have three models that are highlighted on this. The first one says you can see at RCP 8.5. The number represents the amount of radiating forcing, the number of watts per square meter. And then there's 4.5, and then there's lower numbers than that. So 8.5 is where you get the most global warming, because you have the most amount of greenhouse gases. And there are two other names for this. One is business as usual, and the other is worst case scenario. So we're on a pathway right now because of the rate at which greenhouse gas concentrations are increasing, because of increasing emissions, anthropogenic emissions. We're on a pathway right now that could take us back to a global hothouse condition not seen since 55 million years ago within about 200 years. And that is a mass extinction event. And we can go into why that occurs. It's got something to do with chemistry, CO2, and seawater. But there was a mass extinction event 55 million years ago, and the current pathway we're on is artificially reproducing that by producing an atmosphere that looked the way it looked during that mass extinction event.
Very interesting. And that mass extinction event was about how many years ago?
This one occurred about 55 million years ago. This was not the one that killed the dinosaurs. This was a different one that occurred 10 million years after that.
I see. And the dinosaur period is in the blue or in the white blue?
All the way over on the left here. And that was about 66.5 million years ago. And of course, that's when an asteroid about 10 miles in diameter hit the Earth at 50,000 miles an hour and made a crater several miles deep and 200 kilometers in diameter. It was a rain of fire throughout the whole world, a mass extinction. So what happened?
Just so I understand and so the viewers can follow. Yeah. What you're saying on the left of the screen, the red is the hothouse. The dinosaurs existed to the left of that red?
Well, you just find along the time scale about 66.5 million years ago, and you'll see that point. And you can see that the temperature got cool. It was warm, but you can see that there's a downward trend. The temperature got a little cooler. If I could use my mouse, I could point to it, but you can see that spot back there where the dinosaurs were all killed off by this event. But then you can see right after that, peaking at about 55 million years ago, it got a lot warmer, even than when the dinosaurs were around. And that was a feedback event. We don't know exactly what caused it because it was so long ago. But one of the theories is that it was a methane feedback event. So a lot of melting of permafrost, a lot of outgassing of methane, which is a very powerful greenhouse gas, went into the atmosphere, created a feedback. And of course, methane breaks down into CO2 and water vapor over time. But you can see another point where the Earth is quite warm about 55 million years ago. And that was one of the other great dyings that is called. You can look up Elizabeth Colbert's book on this. But what happened there during that event, the Paleocene-Eocene thermal maximum, is that the excess carbon dioxide in the atmosphere interacts with seawater and gets absorbed into the ocean. And it lowers the pH of the ocean. A pH is a measure of how basic or how acidic it is. The ocean is normally, it's basic. It's about 8.5 on the pH scale.
It makes it more acidic, the ocean.
You put carbon dioxide into seawater, you get carbonic acid. And the result of that is that the animals that are at the bottom of the food chain in the ocean that live in these tiny little shells called tests, because the ocean is too acidic, these animals cannot form their shells, and so they die.
So these are the plankton and the algae, or
now these are called foraminifera, and they're like a really tiny snail. Okay, and so they're very small. They're like on the order of about 0.5 millimeter in size. So it's almost like krill. Okay, if you can picture that. So yes. So these animals, they die, and then the animals that eat those dies, and then it ricochets. It just goes all the way up the food chain. And so that event 55 million years ago was a mass extinction in the oceans. It killed off about 95% of the species in the ocean.
Wow.
So what we're doing, if you look all the way over to the right side now, RCP 8.5 takes us back into that same temperature range again.
I see. It's kind of hard for me to see on the screen, but that with the temperature range, there we go. All right. So we're talking about on the far right now.
That's right. And those, you see the different models, 8.5, 2.6, 4.5. That RCP stands for Representative Concentration Pathway. And it is a socioeconomic model that is fed into a physics model of the atmosphere. And so what they're trying to do is to gauge what the effect of human emissions are on the concentration of greenhouse gases in the atmosphere. The number corresponds to how much excess heat is trapped in the atmosphere. So right now we're on a pathway that looks like 8.5, which is business as usual. Emissions continue to increase and accelerate, and it's also worst case scenario.
Wow, that's really horrific. Let's go to the next slide, engineer, so that the doctor can continue. And so now, what is this slide showing?
All right, so these are feedbacks. Now here's the part about this that makes it difficult, but we're learning, we're getting better at it. The Earth system is forced externally by astronomical variations in the amount of sunlight. I can go into that if you want. I don't think we've got time.
No, I don't think we have time, Doc.
The Earth system is also internally dynamic. It's complex like an organism. And so it's like if you push me, and I'm going to push back. That's a positive. That's a negative feedback. If you push me back too far, you can stop pushing because I'll go over backwards in the chair. That's a positive feedback. So we have negative feedbacks, dampening effects. We have positive feedbacks, which are accelerants. And this lists some of the feedbacks in the system that we know of and the temperature range at which they're likely to occur. So we are blowing through about a 1.5 degrees C increase in temperature right now. And you can see that there are several up there at the top, 5 or 6, that are likely to occur as we go through 1.5. By the time we reach an increase of 2.0, which we're likely to hit, I would think by the end of the decade, maybe by the middle of the 2030s, you're going to see a lot more of these feedbacks start to kick in. Now, you can also make out that there's a lot of uncertainty, and that's because this is a complicated thing, and we're learning. But most of these are positive feedbacks. There's a couple of negative feedbacks in there. By that I mean,
now you listed them on the graph, but just if you could verbally, just give me very quickly, because we're getting near the end of the show, and I want to make sure we get to a conclusion. So what are these positive feedbacks that are really not really that good because they're going to damp over everything? So what are they?
Well, for example, you melt the permafrost. It goes all the way around the North Pole. You get a lot of methane gas. Methane is 80 times more powerful than CO2 as a greenhouse gas. That's an example.
All right.
So why don't you go to the next slide and we can show you the result.
Go ahead. What's the next slide, engineer, please? Here we go.
This is a graphic from Stefan et al. 2018, published by the Proceedings of the National Academy of Sciences. There's a lot in this picture. I wish I had a half an hour just to talk about this. But let's just take it up to the point where you can see it shows the Earth now and 2 possible futures. One where it says, what does it say again? It says Earth Steward. And this is the one where we go off to the left from the perspective of the picture. And human beings take on a kind of a World War II scale effort to control the amount of greenhouse gases in the atmosphere, to dial them back. We've got to get them way back below 400. We need to get them back to about 350. That's going to be a huge effort. And at that point, we'd be able to restabilize, if we're lucky, in a Holocene-like climate. On the other hand, if we keep going in the direction that we're going in now, and that's the straight line shown in the image here, there's a kind of boundary. You can see a threshold value there. And it's labeled planetary threshold, and it takes us into a different stable state called the hothouse Earth again. So that's a point beyond which the feedbacks become so strong that nothing we can do will slow down the heating, and the Earth will drop into a very stable, hot state, like the event 55 million years ago, and stay there for a really long time.
Now, you know what, Doc, since we're getting near the end of the show, and I see you have such a wealth of knowledge, but I want to make sure that we get to a conclusion because we're at the end of the show. So basically, from what I'm getting, is this is an enemy that we have created, and we need to take a look at this. If I surmise it correctly, that all of the inhabitants, really all of the races, all of the nations, all of the religions need to really wake up and realize that these smaller problems that we complain about and we fight about all day long, that if we're not careful, if we don't give this off to some kind of paranoia, conspiracy theory, planetary theory, that the reality, which some people talk about apocalypse and God doing this, that nature will affect mankind. This may sound like a little bit of a extended show and conclusion on a television show, but to really wake us up, it seems to me that we need to wake up, pay attention to what we're doing with CO2 and temperature, pay attention to the climate change as a reality, and unite as mankind, as we did with the satellites out in the space, take it seriously, not scare everyone to death, but to have a unified purpose that possibly may bring more humanity, a little less technology with all of the emissions and pollutions, bring a real economy that we have life for our grandchildren. Obviously, we're not talking about 10 years, we're talking about a long time to come. But it would be nice to know as a legacy that we did something. Would this be as we end the show, is this a good surmise?
It is. I want to add one short thing.
Yes.
Small tinkerings around the edges might have been affected 30 or 40 years ago. That might have been enough. It is no longer enough. We have waited for so long that now some very fundamental and large-scale changes are going to have to occur. And the most important thing that we can all do is consume less, right? Because every time you buy something, that represents a greenhouse gas footprint. That's a climate change footprint. Consume less, consume local, learn to live within our planetary means, and convince the people in power that have the power to do something about this to actually do something effective, rather than what they're doing right now, which is largely a lot of talk. I mean, I don't want to dismiss it entirely. There's been some good works done, but it's just tinkering around the edges. This has got to be big.
Well, Doc, you know what? You actually deserve much more time. This topic deserves much more time. But we've accomplished a lot. Again, for our viewers, this is not to scare you, but this is so we actually, if you have a problem, we want to deal with it. We don't want to put a Band-Aid over it. And this is not to be a commercial entity or to make a profit or to have someone win a political race. This is about humanity and paying attention to the future. We're not going to fall off the square of the earth like Magellan never did. The earth is not the center of the universe, which Copernicus found out. Let's not find out too late this time. Doc, thank you so much.
Thank you. Thanks for having me.
Great show. Way too much to put in 25 minutes. For those of you watching, let's take heed of this. Let's do what he said. Let's wake up our leaders. Let's wake up our globe. Let's stop fighting over ridiculous minutia when really the future of mankind is at stake. I hope you take this show seriously, not as something paranoiacal or to scare you, but so we can work together on a much higher goal and preserve this beautiful planet. Thank you for tuning in, and we'll see you again on the next episode of A Time for Truth show.
This show was sponsored by A Time for Truth Foundation Incorporated as a community service.
Sometimes life can be so damn hard. You don't know where to go. Everything keeps falling apart. Yeah. You try to do your best, but only God knows that you've given everything you've got, but the world takes you down. You just keep moving on. Let your feet